pressure increased, and it produced a very high magnetic pressure, leading to explosions. This was confirmed by many two-dimensional and three-dimensional calculations. Here, as an example, you see the plot of energies. This is energy of explosion, which reaches 5, 10 to 50 ergs, but it can be also easily increased several times for different boundary conditions. The magnetorotational instability is very important here because it shortened very strongly the time of development of explosion, increasing exponentially the magnetic fields, poloidal and toroidal. And this is a numerical picture show the development of this instability, which is schematically shown here. So you have vortexes. These vortexes increase magnetic field. Poloidal, then it is also increased by twisting, and so this self-accelerating process leads to exponential growth of magnetic field. So here the diagram showing the distribution of pulsars. This is the main single pulsars. This is recycled pulsars with very low magnetic field. And we have several very high magnetic field pulsars also, which are don't show any traces of explosions. Gamma ray bursts were discovered, first publication in '73, and there are many models appeared, more than 100 models, mainly connected with galactic origin of magnetic of the burst, accretion, explosions, and so on. And here in this paper, we have summarized several models, including the model where gamma ray bursts were connected with supernova explosion due to neutrino flux is transforming into gamma radiation. What is actually now considered as a central engine. So there are, after discovery of afterglow and discovery of the high redshift events, the main models of galactic origin were forgotten, and several other very highly, rather unusual models have been suggested. First is hypernova, which is very powerful supernova, explosion of helium star, and so. Then Usov in '92, before finding, he was the person who, together with Prelutsky, suggested that in the early time, suggested that gamma ray bursts are a cosmological origin, connected with the nucleus of active galactic nucleus. And so he suggested a newborn pulsar, which is very rapid in high magnetic field, and it loses its energy by dipole radiation very quickly and produces a very strong flux of energy, giving a burst. And this model related to Woosley and co-authors, which considered formation of a black hole, massive black hole surrounded by magnetized accretion disk, and gamma ray bursts are connected with these processes inside this disk and falling of the disk into a black hole. And this model is now the most popular. And the calculations of this model, rather, I think, more extended, have been done by Barkov and Komisarov. This is how it happens. This is accretion disk. Here is black hole, and in the process of differential rotation, magnetic field is increasing and giving a start to this collimated jet, which is usually connected with the gamma ray burst, because if it's not collimated, then it should have an enormous energy, which is absolutely impossible to imagine. Energy exceeding rest mass energy of the sun or any other star. several times. So in order to have less energy output, the gamma ray burst should be definitely collimated. Also, there are several two more exotic models. It's a magnetized disk together with Bland-Fajanic mechanism. It's slightly something intersect with Woosley mechanism, and vacuum explosion of strongly charged, electrically charged black hole. It's a so-called diodosphere explosion, which is suggested by Ruffini. And but the main problem here is how to form such a highly charged black hole. So among about 4,000 gamma ray bursts, now it's maybe more, it's about several years ago, maybe 10,000. And these gamma ray bursts are divided into two groups, short gamma ray bursts and long gamma ray bursts. And maybe they have different origin. At least part of these short gamma ray bursts are definitely connected with quite another object, soft gamma repeaters, giant bursts from soft gamma repeaters. They have very high redshift, up to 9. This is 8. It's maybe old, but now it's up to 9. And as I told you, origin may be different. What is interesting is to look at the dependence of the maximum spectra in the gamma ray burst as a function of redshift. As we heard from previous talk, this maximum corresponds to 200, 400 keV. So it means that if gamma ray burst is at 9, Z9, that it should move to 20, 40. But I don't know, was this statistical analysis done or not? So the afterglows are connected with different reasons. The most popular is the fireball, which is formed by the shock in the surrounding medium, and this surrounding medium define the light curve together with the collimation angle. But there is another source of afterglows. It's afterglows from the heated gas, because the gamma ray, if you consider only the gamma ray flux, then if it's surrounded by the dense enough like molecular cloud, then the heating of this cloud and subsequent cooling will give you also some kind of optical and ultraviolet afterglow. And it was, we first have calculated this for one-dimensional spherical symmetrical case in 97, and later in two-dimensional model with Barkov, where we considered different kinds of structure of this cloud, non-symmetrical, and with different structures, you can find a very different kind of light curves in duration and in form. And here there is a movie which is not working, maybe later I show. And also what is interesting, this radiation of in this molecular cloud, if it's very dusty, can lead to formation of the infrared afterglow without any optics. This was observed in this gamma ray burst, where only infrared afterglow was existed without optical afterglow, and we explained it by radiation of this cold molecular cloud, and gamma ray burst is slightly heating this cloud, but not evaporating dust. And in this regime, you will have a infrared light curve without optics. Most interesting for the origin of the gamma ray burst is a prompt optical emission, because what we see in the larger times is connected with surroundings, but the prompt optical emission is should tell us something about the nature of the central engine. So the first prompt emission was found here, in this 99, and it started after about 100 seconds. And this light curve was very important, but it has very small number of points. It's not shown here, but there are only 3 points, so we can put only triangle for this gamma ray burst. And what was clear is that the luminosity drops very quickly in the prompt emission. The most important data about prompt emission was obtained in this system called Tortora. It's camera which was originally installed in Caucasus Mountain, a special astronomical observatory, with very wide field of view, You see 600 square degrees with good time resolution, 0.1, and not very high limiting value, but it seems to occurs to be enough. And the second example, such installation was done in Chile together with the Italian telescope REM, which also was supposed to observe gamma ray burst. And due to very wide field of view, the gamma ray burst, well, later you will see it. This gamma ray burst was observed not only not after glow, but was the whole light curve before the beginning of the burst was also visible. And it leads to a very important discovery showing that the prompt emission and afterglow has absolutely different origin. You can see it. This is the optical light curve. This optical light curve, not, and it's called naked eye gamma ray burst because you see it's brighter than 6 magnitude. And you see that this light curve repeat almost exactly the gamma ray burst light curve. And it lasts about 60 seconds. And then it drops very strongly down. You see it's after 60 seconds it drops down up to 13, and after 1,000 seconds it's practically only for larger telescopes. So the prompt optical emission is very strongly correlated with gamma. What it means? It means that the surroundings are not important, that it's transparent for the optical radiation, because you see light curve in optics almost exactly repeating the gamma ray burst. Therefore, what happens later in these afterglows, it's a questionable, because you need a lot of matter to see it, and it makes problems for this canonical model.
Unfortunately, there's a counterexample of one that's clearly not correlated. It's also...
No, I speak about this particular model, about this particular event. I'm not speaking about in general.
Okay.
So what else is important is that the afterglows, if there is a collimation, the exact comparison with gamma ray burst shows that this prompt optical emission should be collimated in the same way as gamma radiation. And that means that the naked gamma ray burst optical events, estimation of number of these naked events decreases strongly, so it's not surprising that we have not seen any naked afterglows, because they are much less luminous. Only the later afterglows can be non-collimated. That's all what I wanted to say about gamma ray bursts. Now I want to attract your attention to soft repeaters. Soft repeaters initially were discovered by Mazet's group as a normal gamma ray burst from direction from large Magellan clouds, and initially it was supposed that it's just contamination. But after some years, after maybe tens of years, people start to believe that it's really exists in this large Magellan cloud, and since then, Mazets first, and then later Batsy, people discovered about 10 or now they increased the number of these gamma ray bursts. What is characteristic of the and they were divided into separate division because they were recurrent. All gamma ray bursts are single events, but these were recurrent. So it was definitely objects which produces these events. After discovery of period, which was first discovered in this large Magellan cloud, most of the soft repeaters have periods between 5 and 8 seconds. So they are very slowly rotating gamma ray bursts, slowly rotating neutron stars. And the energy, rotational energy, was definitely not enough to produce such a strong explosion. When P dot was measured and P dot was connected with rotational energy losses, which are not really correct. It's not correct when you consider source which is very strong, and only small part you connect with the losses of angular momentum. But nevertheless, the magnetic field there was about 10-15 Gauss, and these objects were called magnetars. We see now that this concept of magnetars is very faint. So I think it's slowly dying, because there are many observational results showing that this activity is not connected with strong magnetic field from one side. From another side, there are several radio pulsars with such high magnetic fields. And third is that pure theoretical reason. If you have very strong magnetic field, then in order to annihilate magnetic field, you need to move it, like in the sun. Convection approaches to magnetic field lines and they annihilate. But in this case, magnetic field forces are much larger than any other forces. So even star quake is not clear what to do it. What is characteristic to these soft repeaters is each of them has one giant burst where their luminosity increased many orders of magnitude. And due to this, we can expect that short gamma ray bursts, which are observed, at least some of them, are just giant bursts from these soft repeaters situated in the nearest galaxies. This was suggested in 1999 in my paper and paper of Mazets and all others, several his collaborators. And in Mazets' group were discovered at least two short gamma ray bursts, which may be, for Andromeda is probably very certain that they are connected with giant bursts of gamma ray, soft gamma repeaters, with energy of the same order as energy of estimated for galactic events. Here I show the example of pulsars with very high magnetic field. This is 4×10⁻13. This is even larger, about 10⁻14 Gauss. This is also, you see two radio pulsars with magnetic fields with magnetar fields. Means that this is radio pulsar, but not magnetars. And also you have periods in these radio pulsars of the same order as magnetar periods. For example, this period 8.5 seconds. It's a pure normal radio pulsar without any explosions, with a period 2.8 second, a period 8.5 second, and which has no explosions, just radio emission, and that's all, like normal pulsar. So this is, it was suggested that you have a limiting period after which pulsar are dying, but discovery of this pulsar leads to this title of the paper of Manchester and all. So soft gamma repeaters, I list here several most famous soft repeaters, and the recent discoveries show that that soft repeaters should have very high magnetic field, even estimated not correctly, is violated in this pulsar. So you see that in this particular soft repeater, which is also just pulsar with the period, I don't know, about 5-7 seconds, not important. Magnetic field doesn't exceed 7, 10 to 12 Gauss. Means it has very low magnetic field for the magnets. No normal pulsar magnetic field. Therefore, these are light curves of the pulsar. Therefore, the connection of pulsars of soft repeaters with magnetars is even shaking even stronger. This is one of the most striking observations of soft repeaters, which permit to find out its absolute luminosity. Soft repeaters' giant bursts are so strong that all detectors are saturated, and nobody observed the maximum. And so nobody knows how high is this maximum. This is the first case where this maximum was observed. It was observed indirectly by observation, by a reflection signal from the moon. The main detector is on the American satellite WIND, but at that time the second detector was a Russian satellite Coronas, and this Coronas detected the signal which was exactly in time of this giant burst. And when analysis showed that it detected the signal reflected from the moon because it was in the shadow of the Earth when it happened. So this is reproduced absolute light curve of this burst, and it shows that permit to estimate the absolute luminosity. This is the paper of Duncan Thompson, where they have considered magnetar model. Here I want to show that this interpretation of prompt P dot is not good, because these objects has very variable light curve before the burst and after the burst. You see a change of the. So how to measure the change of derivative of the period is a very big error, and a jump in P dot which is never observed in radio pulses, such a big jump. Also, it was claimed that it was observed cyclotron line, and if it belongs to proton, it has very high magnetic field. But maybe it belongs to electron, then it's quite normal magnetic field. What is most important from point of view of interpretation is that if you have very high magnetic field and strong magnetic wind, then it can produce angular momentum losses much higher than the dipole losses. So the alternative model of the activity of gamma ray bursts of soft repeater is connected with the properties of neutron stars. The neutron star had outer core, and in this outer core, the composition is non-equilibrium, because formation of the neutron star by contraction going through hot phase or by accretion when there is cold shows that matter never reached its ground state, and if the matter and this connected with very high density, because Fermi energy prevent beta decay and prevent going to the ground state. But if the matter by some quake goes out, then it could be a chain reaction and strong explosion. Not thermonuclear, but nuclear explosion. So we have estimated many years ago, it was at the middle of 70s, we have estimated for that the energy inside this layer could be 10 to 48 ergs, what is enough for several bursts at time. And here this was connected with gamma ray burst. And now I want to show you the what is seems to me a very promising idea. Promising idea is that if you decrease the mass of the neutron star, then this thickness of this non-equilibrium layer is increased. So for example, for 0.5 solar masses, it increased about 10 times. This is bottom of the non-equilibrium layer, it's upper bottom. So 10 times more mass is in this non-equilibrium layer. So if there is something happens, then the radius is also increasing for low mass neutron star. And that means that this neutron star should rotate with lower velocity. Their limiting velocity, limiting angular velocity is decreasing, and also it has a much higher supply of energy.
How are you reducing the mass of the neutron star?
Sorry?
How are you reducing the mass of the neutron star?
This is not a question. I don't speak about it. I say if it has low mass, then it happens. But how you reduce, it cannot be reduced. It can only be formed in this way. Because if it loses eject all the matter, then nobody knows how it happens. No, closed binary system is increasing. Therefore, as I told you, in 0.45 mass of a non-equilibrium is 7 times larger. So we have energy for 1,000 giant bursts from soft repeaters. This is how it happens. Atomic bombs and comes out. It's from my old presentation of '87. And here is explosion. Explosion is also on part of these calculations of shock waves formed during this. It's also very old idea. Therefore, the conclusions. So the gamma ray bursts are cosmological objects of unknown nature. So maybe it's black hole plus heavy magnetized disk. The key information may be coded in the prompt optical afterglow. If you measure polarization and spectra of prompt emission, you can find much more than we now find from thousands of spectra of these late afterglows. So the soft repeaters are highly active and slowly rotating neutron stars. A nominal equilibrium layer is formed in the neutron star crust during neutron star cooling or during accretion into it. And it may be important for glitches, explosions connected with soft repeaters. The mass and energy stored increase rapidly with decreasing neutron mass. And the activity of soft repeaters can be connected with this activity of non-equilibrium layer in neutron stars of lower mass. As I know, observationally, the lowest neutron star mass is less than 1 solar mass. Observation. Thank you very much.
Thank you very much.